Have Ulysse Gimenez, Data Science Director from BioSerenity. Welcome to the stage.
Thank you for the introduction. Hi everyone, I'm going to take you on a 10-minute journey in the world of electroencephalography. So EEG is a way to measure the electrical brain activity. It can be applied in different domains, but we are going to focus on the medical domain here, and especially in the domain of neurological diseases. There is a wide range of neurological diseases, but there is one thing that many patients have in common. They are waiting a long time to have a diagnosis. This is due to different factors. One of the big reason here is the shortage of neurophysiologists. So this is the context we are working at BioSerenity. Our main challenge is to change the way EEG is done using AI. We have two main ambitions. The first ambition is to accelerate the existing diagnosis, the existing practice. We want the physician to focus on the segment of interest, for example, and we want to get rid of all repetitive tasks. Our second ambition is to improve the diagnosis. We are developing biomarkers that will help in the future to have early diagnosis, but also to monitor the patients and really change the way EEG is used at the hospital and at home. This remains a big challenge because this is EEG signal. I'm working into this field for 10 years and I'm still not really able to understand it and to read it. The signal is chaotic, it's very noisy, and we have difficulties to gather big amount of data with annotations. To tackle this challenge, what we do is developing EEG foundation models. Foundation models are AI models that happened 5 to 10 years ago and had a big impact in the AI world. This is what you have behind LLMs, for example. The idea is to train a model with a lot of unlabeled data, and the model will learn the representation of the data. If we keep the analogy with language, what it's going to do is to learn the grammar or the way you can build sentences. Once you have this foundation model, you are able to create new use cases quite easily. You only need a small amount of data, a small compute, and it can go fast if you compare to classical approach and deep learning. We have developed for EEG foundation models, and the first one was published beginning of the year. So it's a preprint journal. And if we sum up, there are 4 main steps here. The first step is the data preparation. It's quite common in any AI project. After this, you have to train the model. It is done with tokenization and mass token prediction. And last, once the foundation model is trained, you can derive different downstream tasks. If we take a closer look, this is what is going on. So for the tokenization, you go from the EEG signal. It's a temporal signal. We are going to cut it into 1 second batches, and we are also going to separate the different channels. You are going from the temporal signal to frequency signal. Once you have all these patches, you can set it to a vector quantized variational autoencoder. It's the blue architecture here, which is going to help us to build the codebook. A codebook is like a dictionary of 8,000 vectors. It's 8,000 tokens that will represent the EEG variability the model has seen with all the patches during the training. Okay, once we have this codebook, we can go to the next step. This step consists in training the green model here. This is the foundation model. We have the same architecture than before, and we use a task which is quite common in AI, is getting the same type of data but masking a part of the batch. The goal of the model is to predict what is the token behind each behind each mask. Excuse me. Doing this is going to learn the EEG representation. It's going to understand how the brain waves are propagating over time or propagating over space. Okay, let's say we're done with the foundation model. You have your green model. It is trained. You don't have to touch it anymore. Now, what we do is that for each new use case, you have to get labeled data corresponding to the use case, and you are going to fine-tune the prediction head. In this paper, we showed different downstream tasks in which we did this, and we compare in blue the Biosanity E1 model and compare to same model training from scratch or deep learning models. We saw that we have better performance with Biosanity E1 model, and what we saw also is that if you take a look at low data regime, if you get low data for the fine-tuning, the impact is even greater. This is quite important for us because we want to work on pathology where you don't have much data to train. Here is another paper we have in May. So basically, we are using the same foundation model with a different use case. We want to separate healthy patients to patients having a neurological disease. The architecture is the same, and for the prediction head, we use a database of 4,000 records that is come from Bioserenity Medical Services. It's quite huge database here. And for the test, we use 200 records that have been annotated by 3 neurologists, so we can build a robust consensus. If we take a look at the results, we can see that Biosanity E1 is getting better results than other deep learning models. And this is true even with a large database that has been trained used for the fine-tuning. Actually, here, I don't show it, but we saw that we have equivalent or even better performance than individual neurologists compared to the consensus. This algorithm it's good, but it's not only an algorithm for a paper or for a presentation like today. It's going to be a medical device soon. We are undergoing the CE marking and the clinical study, and it will be deployed into our products next month. So next year we'll have thousands of patients having this algorithm with their EEG. We are quite proud about it, and being so fast into delivering the algorithm is also due to the networks of neurologists that are working with us. They are helping us to co-develop the algorithm and to make it real. Here I have a video to show you how it is integrating into our products so you can better understand. Okay, so this is the iSCAP. It's a medical device we developed at Biosanity. You can record the EEG with, you can see that it's quite comfortable, and you can have it for 2 days at home, for example. The EEG is sent to the cloud. We are running the AI, and the physician will receive everything. He will have his platform like this, and this platform contains AI tools like you can see here. We have buttons. Here it was a button where you can see the diagnosis, but we have also other support like events we can put into the signals. To our knowledge, it's the first time that we have EEG algorithm derived from foundation model, which is CE marked and used as a medical device. As you know, as you understand, maybe we want to deliver a lot more biomarkers and algorithms we are working on. If you want to know more about it, please go to the speech of Pierre Emmerich, our CTPO, tomorrow. And maybe 2 last words. If you are working in EEG and you want to test our model, please come to see us. We are really open to partnerships. And the last word to thank the team and the partners. Thank you, everybody.
Thank you.